Hello, my name is Jared Skeens, and welcome to the Zoom room. Today, we would like to look at mechanics, distance, velocity, and acceleration, part 2, calculus. Now, in part 1, we looked at SUVAT, which is the algebra formulas for distance, velocity, and acceleration. And today, we want to look at the calculus formulas for it. So again, remember that the key to these question types is acceleration. The first thing you need to establish is which set of formulas are you working with. So if your acceleration is 0, meaning there's no acceleration at all, or it also means your velocity is constant. So if your velocity is constant, you're not accelerating. Or you have a constant acceleration, then you're going to use the SUVAT formulas. And we looked at 4 of them in part 1. However, if your acceleration is a function of time, then, which means your acceleration is constantly changing. As time changes, your acceleration changes. So if you're constantly changing acceleration within a particular interval, then you're going to use the calculus. Calculus is what allows us to work with changing something that's changing. So that's our first key. And then, of course, again, just a reminder, the second thing you should do is draw a diagram, a quick sketch to help you, give you some sort of spatial orientation, which is really helpful for these kind of physics-oriented math questions. So let's look at our calculus equations or formulas. It's really not formulas, it's more or less relationships, calculus relationships between actually displacement, velocity, and acceleration. So you should have learned this already in Pure 1 math, the Pure Maths 1 content, where you learn derivatives and integrals. If you have not yet learned derivatives and integrals, you should probably do that first. So if you start with a position function or your displacement function, so we use the little letter S to represent displacement in terms of time. So this is going to be an equation, your displacement as a function of time. And if you derive that, the derivative of the displacement is velocity. If you remember back in IGCSE math, if you had a distance time graph, the slope of the graph is your velocity. And slope in Pure Maths 1, you learn by taking the derivative, the change in y over change in x, or the dy over dx. So the derivative gives you your velocity. Same thing with the velocity time graph. If you have a velocity time graph, your slope is the acceleration. So again, slope is derivative. Your dy dx, the derivative of your velocity function, will give you acceleration. So this is what you're going to have to use to develop your different equations. If they give you any one of these 3, you can develop the other 2. Now, if you need to go the other direction, if you're given the acceleration in terms of time or as a function of time, which is our kind of key to understanding, we need to use calculus and not SUVAT, that if you want to go from acceleration, then you need to integrate your acceleration function to get your velocity function. And then don't forget the plus c, because these are indefinite integrals. So with an indefinite integral, you need the plus c. Also, if you take and you integrate your velocity function, then you get your position function or your displacement as a function of time. And then again, don't forget the plus c. Now let's just talk about that plus c here really quickly. Back in Pure Maths 1, when you learned integration, and you learned that you put the plus c with an indefinite integral, Usually, the Cambridge question will provide you with a point that is on your function that you're finding, and you just plugged it into your x and y, and you can find the plus c. Well, in this application, they're not going to explicitly give you, okay, here's a point, and you know that you plug it in to find the plus c. You're going to have to think a little bit. You're going to have to think about the initial conditions. If your initial position is at the origin at when you start, in other words, if your t equals 0 and you're at the origin, then your c will be 0. You only have a plus c as if your particle is not starting at the origin being your point of reference. So if you're not starting at your point of reference, then you will have a plus c. You're going to have to figure out from the context how to find that. But if you are at the origin at t equals 0, then you don't have a plus c, or your plus c is 0. Same thing with velocity, is if at the t equals 0, if at your starting point, if you have no initial velocity, then your c is 0. If you have an initial velocity from the very beginning, then that will be your plus c. So again, it's not like Pure Maths 1 where they explicitly give you a point to plug in. You're going to have to look at the context of the problem to determine whether or not you have a plus c. So for this will be an initial starting point that is not at the origin. This will be initial velocity. So in other words, you're not starting from rest. If you're starting from rest, you have no initial velocity. Okay, so you're going to have to do a little bit more intuitive thinking for it, because it's not explicitly given. Okay? So these are the formulas you're going to use. So again, as you approach a Cambridge question type, it should be quite obvious that the question is about distance, velocity, and acceleration by the way it asks the questions. Find the velocity, find the acceleration, find the distance. So it's very important at the very beginning that you determine, are you dealing with the Suvat algebra equations, formulas, or are you dealing with these calculus ones and you have to derive the other equations yourself? And of course, draw a sketch. So let's get started so we can see what this looks like, and I'll set up the first problem for us. Okay, I have the first problem set up for us, but before we get to the board work, let's look at the problem itself and see what it says here. It says particle P travels in a straight line from A to B. The velocity of P at time t seconds after leaving A is denoted by the velocity in meters per second, where V equals 0.04 t cubed plus ct squared plus kt. Particle P takes 5 seconds to travel from A to B, and it reaches B with a speed of 10 meters per second. The distance between A and B is 25 meters. So the first question, notice it's 6 points, which means you're going to have to do a little bit of work. Find the values of the constants C and K. So here you can see our velocity function, C and K. Now let's look at just the second question just to get it in our head. We also need to show that the acceleration of our particle P is a minimum when t equals 2.5, in other words, at 2.5 seconds. So the first thing we need to do before we even go to the board work is we need to figure out, are we working with Suvat or are we dealing with calculus? Obviously, we're dealing with calculus because this is part 2, calculus. Part 1 was on Suvat. But how do you determine it from the question? Well, notice it gave us velocity as a function of time. And the velocity is cubed, t cubed, it's a cubic, which means if you take the derivative of the velocity, you're going to get a quadratic, a t squared, which means your acceleration will be a function of time. So you should think, what is the relationship of velocity to acceleration or position function to acceleration to determine if your acceleration is a function of time or a constant. So because velocity is cubic, means acceleration is quadratic, and it is a function of time, therefore we need to use calculus formulas to help us. So now we can go to the board, and the second thing that we want to do is draw our diagram. And the diagram is just a sketch. It doesn't have to be fancy. Here is point A and here is point B. And I've put down the information that they provided. They provided for us the velocity function. So I wrote that down. They told us that the distance between A and B is 25 meters. They also told us that it takes 5 seconds for particle A to get from point A to point B. And when it arrives at point B, its velocity is 10 meters per second. Okay, so this is information provided. Now remember, it wants us to solve for C and K. And we have two variables in the same equation. That means we need to come up with two separate equations so that we can solve these two variables. We need to do simultaneous equations. So because it gave us distance, let's go ahead and find the distance formula, meaning we have to integrate our volume. So if we integrate our volume, we will get displacement. And remember, when you integrate, you add 1 and divide by the number. So when we add 1, we get 4. When we divide by 4, we get 0.01 t to the 4th. Then we add 1 here and divide by that, so we get a third c, because we have to divide by the 3, t cubed. And when we add 1 here, we get a square, so that's k divided by 2, t squared. Now we need to think about the plus c. Is there a plus c or not? They don't give us a point to plug into it. So we need to think, when t is 0, was our particle at the origin? Yes, it started from A and it went to B. So we don't need a plus c because our initial conditions at time 0, we started at the origin. The plus c is only if you're starting at a point that is not at the origin. If you also look at the velocity, there's no constant at the end of the velocity, meaning your original velocity was 0. There was no, if you put time 0 in here, means your initial velocity was 0. So you can also tell your initial velocity from this, even though it doesn't directly state it. Now we've got two equations, and we need to find C and K, and the variables that we're given are T, V, and S. So if we look at this one, we're given a displacement after 5 seconds, and we're also given a velocity after 5 seconds. So what we want to do is we want to plug in our 5 seconds and our 25 into here. So we get 25 equals 0.01 times 5 to the 4th plus c over 3 times 5 cubed plus k over 2 times 5 squared. And when we work all of that out, so I'm going to jump ahead a little bit. When we work that out, we get 25 equals 25 fourths plus 125 thirds c plus 25 halves k. Now for me, I don't like all these fractions here, so I'm going to multiply everything by 12 to get rid of the fractions. And when I multiply by 12, that makes 300 equals 75 plus 500C plus 150K. And now when I look at that, I realize that everything is a factor of 25 in it. So I'm going to divide by 25. Maybe I'll make this red so that it stands out. Multiplied by 12. Here we're going to divide everything by 25. We choose these parentheses so you don't get it confused with the original. So I'm just doing a little numbers playing here to make the equation a little simpler. So multiplied by 12, reason to get rid of the denominators, don't like fractions, and also notice that everything is a factor of 25. So if we get rid of that, it will simplify it a lot. And so that's going to bring us down to 300 divided by 12 is equal to 25. So here we have that brings us down to 12. Where do we go here? I lost track of my, oh here, I guess 25. Well, we'll take the, when we divide by 25, we get 12 and 3, okay? Get 12 and 3, and then if we subtract the 3, that's going to give us 9, okay? And then when we divide 500 by C, we get our 20. 500 divided by C is 20. So we end up with 20C plus 6K equals 9. Why 9? Because we're going to subtract 3 from both of those. So what I'm doing is combining those numbers there by subtracting 75, whether you subtract first and then divide by 25 or divide by 25 and then subtract, you get 9. So what I'm doing is I'm setting it up as a linear equation in terms of C and K. Now we want to do the same thing with our velocity with 10 at the front and plugging in our 5. So when we do that, we get, I'm going to do it here on the side so we have room, 10 equals 0.4 times 5 cubed plus 25C plus 5K. Okay, and this reduces to just 5. So we get 10 equals 5. When you do that on your calculator, you get 5 plus 25C plus 5K, which gives us 5 equals 25C plus 5K. Notice everything is divisible by 5. So if we divide by 5, so some of your work is just simplifying. We get 5C plus K equals 1. 5C plus K equals 1. Now, when we look at this equation with this one here, we see the C's are lined up, the K's are lined up, and our constant is lined up. What we want to do is we want to get a coefficient that's the same. You could solve for K and substitute. If you want to do the substitution method, you can just solve for K and substitute it here. I like the elimination method. So what I'm going to do is I'm going to multiply this by 6 so that it lines up with this 6 here. So that gives us 30C plus 6K equals 6. And then what I'm going to do is I'm going to subtract, but because I like a positive variable, I'm going to subtract upwards. So this arrow here simply means I'm subtracting going up instead of down. So we get 10C equals a -3. 6 minus 6 is 0. The k's cancel. 6 minus 9 is -3. And now I just divide by 10. So I get a -0.3 for the c. And then when we plug that back into here, a -0.3 times 5 is a -1.5. So that means k, when we add the 1.5 over here, k is 2.5. So c and k, there's our two answers. Notice that most of the work was just simultaneous equations of algebra. I even had to kind of find where I was at on my paper there in simplifying this down. So it's just kind of a big simultaneous equations algebra problem, but you need to be able to interpret the meaning of position function, velocity, derive it using calculus, and realizing you have two variables, so you need two equations, one of them being a distance equation because it gave you distance, and one of them being your velocity equation because it gave you velocity. Once you understand that, then you've reduced it down to just algebraic simultaneous equation problem solving. And it takes a little bit of time because of these numbers involved, but it did break down okay. And we still ended up with negative and positive decimal values, but there's no problem with that. So this is the correct answer. And now it wanted us to show that the acceleration was minimum at t equals 2.5. Now it says to show. So that means we need to end up with the t equals 2.5 as our answer, but it said to show the minimum of acceleration. So what we want to do is we want to first of all find our acceleration. So we're going to take the derivative of our velocity function. So our acceleration would be 3 times 0.04 is now 0.12 t squared. And we already have our c as a -0.3, so this is now a -0.6 t. And then our k is 2.5, so it's just plus 2.5. That's our acceleration. Now, so by just deriving the velocity function and plugging in our values for c and k, so you can't do part I without getting this correct. If these numbers are not correct, then you won't be able to show it. So it is kind of a good double check. If you get the right answer, then you know you did the first part right. So we just derived it, multiply, subtract 1, multiply, subtract 1, multiply, subtract 1. The t goes away for this last one. Now it says to minimum or maximum. Anytime, if you remember from Pure Maths 1, anytime you want to find the minimum or maximum, you set the first derivative equal to 0. It's called your stationary points. So if we're going to find the minimum of the acceleration function, that means we need to derive it again. We need to find the derivative of the acceleration and then set it equal to 0. So if we take the derivative of that, we get a prime equals 0.24t minus 0.6. And then the 2.5 goes away because the derivative of a constant is 0. And then we want to set this equal to 0. So that gives us 0.24t equals 0.6 by adding that 0.6 to the other side. And if you take your calculator and you divide 0.6 divided by 0.24, what do you know? You get 2.5. So our t equals 2.5 is our minimum. And you don't have to prove that it's a minimum or maximum. it's already given to you or wants you to show that it is a stationary point. So we proved that our minimum acceleration is at 2.5 seconds in this segment. Between A and B, halfway through is going to be the slowest acceleration point for that. Okay, so that's how I would do the first one. Let's move on. Let me set up for the second one. Okay, I've set up the second problem. Let's take a look at it before we get to the board work. And it says the particle P moves in a straight line from a fixed point, O, the origin. The velocity, v meters per second, of P at time t is given by the equation here, v equals t squared minus 8t plus 12. Here's the domain statement, meaning we're only looking at the section from time 0 to 8 seconds, including the 0 and 8. So first question, find the minimum velocity of particle P. And then the second question is find the total distance traveled by P over this interval of 8 seconds. Notice it's 7 points. That means there's something tricky going on here. There's going to be some work that we're going to have to do to figure it out. So it's not quite a simple distance problem because it's 7 points. So we're going to have to work at this and see what's the trick to this. So let's find the minimum velocity of P. So let me go back to the board here so that we can do some work. And the first thing that we start with is, well, is this calculus or SUVAT? So if you notice, v equals t squared minus 8t plus 12, velocity is a quadratic. So if you derive velocity to get acceleration, acceleration will be linear. We'll go from second power down to first power. But the t still shows up, meaning that our acceleration is a function of time. And so this is a calculus situation where we use the calculus formulas. So that's the first thing we need to establish. So in that distance question, we're not using the SUVAT distance formulas. We're going to use our calculus for that. Also, just to notice is because this plus 12 is here at the end, that means that wherever our starting point was, had an initial velocity of 12 meters per second. So that's something you can deduce from here as well, is your initial velocity would be, if time is 0, then your velocity is 12 meters per second. Well, let's start by finding our minimum velocity. So again, minimum and maximum means, especially in the using calculus, means the first derivative set equal to 0. You're finding your stationary points. So if we do our first derivative, we get, I'll put it over here, A equals 2t minus 8. We want to set this equal to 0. So we get 2t equals 8. And so we get t equals 4. So at 4 seconds, we will have our minimum velocity. So let's plug that in to see what that is. So we get our v equals 4 squared minus 8 times 4 plus 12. So we get 16 minus 32 plus 12, which is a negative 16 plus 12, which is a negative 4 meters per second. Now, we should take note of this. Some students struggle with these physics application because of the sign. So you need to understand that if you're dealing with the position function, a positive value means away from like to the right or in one direction from the origin. A negative displacement would mean in the opposite direction. So positives and negatives are orientation. So positive displacement, one direction from your origin, negative displacement, the other direction from your origin. Now, with velocity, a positive velocity means you're traveling away from your point of reference. A negative velocity means you're traveling toward your point of reference. So in other words, we've got a situation here where our particle P is actually going back toward the origin. So when our velocity is at its minimum, it's actually turned around and went back the other way, is what that means. And acceleration, also, if it's positive, it's like pushing you away from the origin. If it's negative, it's pulling you back towards the origin. So that's an important thing to understand is the signs. Why is that a negative 4 meters per second? Okay, now, since it means it turned around, in order to turn around and go the other direction, it means your velocity had to stop. You don't just, you don't turn around without stopping first. So what I would recommend is once I realize that this particle is going back and forth, the question naturally is how many times has it went back and forth? Because the next question is asking about total distance. And if you change directions, it means you're going over the same ground more than one time. So what we're actually doing is we're adding up displacements, but we need to know how many displacements are we working with. So every time your particle turns around, the velocity is 0. So what we want to do is we want to come up here, set our velocity equal to 0, and we can factor this. Factors of 12 are 1 and 12, 2 and 6, and 3 and 4. But the 2 and 6 is what adds up to give us 8. So our velocity is t minus 2 and t minus 6 is 0. So that means at t equals 2 and at t equals 6, our velocity is 0. It stopped, meaning it's going to turn around and go the other direction. You can also think of this as a parabola. Okay, so let me draw over here in the corner. If you have a parabola with values of 2 and 6, that means we got a graph like this. So notice you have positive velocity, negative velocity, and positive velocity. So it started going away from the origin, stopped, turned around, went back towards the origin, stopped again, and then went away from the origin. So at the points 2 and 6. So what we want to do is we want to break up our time into 3 time segments so that we can find the displacement while it's going in the same direction and not doubling back on itself. So what we want is we want to look at our time segment from 0 to 2. That is, while it's going away from the origin up until it stopped. So from 0 to 2. And then we also want to look at it from 2, and I won't put the equal to on this, until 6, where it stops again as it's going back toward the origin. And then we want to look at it from 6 until 8, where it stops, or where we're done over this time period, okay? And displacement deals with the position function. So to find the position function, we need to integrate our velocity. So when we integrate our velocity, we're going to get, we have to add 1 and divide. So 1/3 t cubed, add 1 and divide, minus 4t squared plus 12t. We're going to have to think about the plus c here to get that plus c. Well, if we started at the origin if we started at the origin, is when you read the question, you have to ask yourself, what is happening at t equals 0? Well, if we read the question, maybe we should go back just so that you can see for yourself instead of just me saying something. Notice it says particle P moves in a straight line from a fixed point 0. Okay, so it went from 0. So since it started at the origin, then that means we don't have a plus c. Okay, so it's important to establish that plus c. So we don't need the plus c, so I'm going to erase it. But you do need to mentally think about it. Are you at the origin or not? Now, it started at the origin, but it did start with an initial velocity, right? The initial velocity was 12, but it did start at the origin. So it went for 2 seconds, then it went back, and then it went again the other way. So we want to find out the total distance that it went. So we're going to find the displacement in each of these 3 sections. So from 2 to 1. So how do we do that? Well, just like when you integrated in pure mass 1, we now have bounds of integration, basically. So we want to evaluate it, our position function of 2 at 2 seconds minus what it was at 0. And then we're going to do 6 minus 2 and then 8 minus 2. So when we do this one, our position function of this, here we have 2 cubed is 8/3 minus 4 minus 16 plus 24, and then minus, when you plug in 0, obviously 0. And when you get all of this one, for that, we end up with 32/3. Our displacement is 32/3 when you combine that together. So 8/3, you should do it on your calculator, follow along, making sure that you understand what's going on. There you go. You see the 32/3 when you combine that. So that's our displacement in the first 2 seconds. It goes 32/3 of a meter away from the origin, stops. Now it's going to turn around and go back. So now we're looking from 2 to 6. And we want to take 6 minus the 2, the further minus the closer. And so when we get this, we're going to end up with, and you can do it in your calculator, but we're going to end up with a negative 32/3. Okay, so do this in your calculator, plug in the 6, plug in the 2, and just to save time, the answer is a negative 32/3. The meaning is it's going back towards the origin, okay? Then we want to do 8 minus 6. And when you do 8 minus 6, you're going to get another 32/3. Okay? Now don't add these up. If you add them up, these are going to cancel and you're just going to end up with 32/3. You need to think that you're doing total distance. So we have a 32/3 in one direction. Remember, the positive and negative has to do with the direction you're going. So this negative is only directional. So we just want to then to find total distance. The total distance here is going to be 3 times 32/3. Okay, so 32/3 that way, 32/3 back, and then 32/3, forward again. So it went back and forth the same place. And this cancels and gives us a total of 32 meters that this particle has traveled. Total distance of 32 meters. So again, you can do this math work. I plugged in the first one for you, and then you do the same thing for these. to get your total distance. So again, don't allow those positive negatives to confuse you. Make sure you put it in perspective of the reference point, in this case, the origin. So that's our second question. We'll do one more for this video, and hopefully you'll get the hang of how these distance, velocity, acceleration questions work. So let me set up the last question. Okay, are you ready? Let's look at our third question here, our last one for this video. And we see the particle moves in a straight line. The acceleration, A, in meters per second squared of particle P at time t is given by A equals 6t minus 12. So right away, notice that acceleration is already given as a function of time. So we already know that we're working with calculus right away because A is already a function of time. The displacement of P from a fixed point, the displacement of P from a fixed point O on the line is S meters. It is given that S equals 5 when t equals 1 and S equals 1 when t equals 3. Show that S equals t cubed minus 6t squared plus pt plus q, where p and q are constants to be found. So we need to show this displacement formula, and we need to find the values of p and q. Then it says find the values of t when p is at instantaneous rest, meaning when our velocity is 0. Okay, so let's start with this. Let's go back to the board. And we've already determined that we're in calculus because our acceleration is a function of time. I put the two values down that they gave us in coordinate form, because usually when you draw a distance time graph, the time is the x-axis and the distance is the y-axis. So at 1 second, it's 5 meters away. At 3 seconds, it's 1 meter away. So already you can see if at 1 second it's 5 meters away, but then at 3 seconds it's 1 meter away, you can tell that the particle was moving back towards the origin, at least at one point. Now we want to find and show the displacement formula. So we need to integrate twice. Integrate once to get velocity, integrate again to get acceleration, or to get the position function. So our velocity, when we integrate, we add 1 and divide, so 3t squared minus 12t plus c. Oh, we got to stop and think about this plus c here and come up with what do we do with that. So let's go back to the problem and look at it, because I want you to be able to see it as well. If you look in here, there's no indication as to what the initial velocity is. Remember, the plus c is your initial velocity. And it doesn't give any clue about it. However, when we look at our show problem, we know that that plus c, when we integrate again, is going to add the t to it. It's going to be plus ct. So when we look at the t term, this letter p is our initial velocity. Okay, so when we integrate again, we're going to get the pt. So that means our c should be the letter p. I hope you understand that. And maybe as you see us work it out on the board, it will make more sense. So they don't give us any indicator about initial velocity, so we can't plug in a number. But when we can see, and we'll just go ahead and do position function. When we add 1, we get 3, divide by 3. There's our t cubed. So that was correct. Add 1, we get 2, divide by that, minus 6t squared. Plus this would become ct, but in the thing it's pt. So that means our c, or that p is actually the initial velocity. And then plus c, well, that plus c is the initial position, and that's going to be the q. Okay. So we're just adding in the p and q as the substitutes for those plus c situations so that it matches the equation that it wanted. So again, let's just look at it because I don't want you to be confused. Notice here, s equals t cubed, we have that, minus 6t squared plus pt. So if our initial velocity was p, then it becomes pt and the position function, and then plus q then is that plus c at the end of our position function. So we're able to get that to work, and now we need to find the p and the q. So we've shown this function. Now we need to find p and q. That's what these two are for. This is s and t, and we've got two of them for our two variables. So when we plug that in, we get 5 equals, and when we get 1 minus 6 plus p plus q. That gives us, I'll just put the other one here, a 1 equals 3 cubes 27 minus 3 squared is 9. 6 times 9 is 54 plus 3p plus q. So the two equations that we want from that, 1 minus 6 is a negative 5. When we add that over, we get 10. And here, 27 minus 54 is a negative 27. So when we add it over, we get 28. 3p plus q. So we're going to subtract. We get negative 18 equals a negative 2p. Actually, I like to subtract going uphill to avoid all those negatives. So q minus q is 0. 3p minus p is 2p equals 18. So p equals 9. Meaning that our initial velocity was 9 meters per second. Initial velocity of 9, and since it's positive, it means it's initially going away from the origin there. Even though the acceleration is possibly pulling it the other direction, it's still going away, moving away. Then we need to solve for the q. So if we plug the p in up here, 10 equals 9 plus q, we see that q equals 1. What does that mean? Well, if q equals 1, that means we didn't actually start at the origin. Our displacement started already right here. Our p started here at 1 meter away from the origin. It started going away from it, and it may at some point have turned around, whatever, because notice our velocity is a quadratic. That means it's going to have a positive, negative, positive. So at some point it's going to turn around in there because it's a quadratic function. So we looked at that last time in the diagram. So what that means is it didn't start at the origin, which is important. But here we answered the question. We showed the position function. We had to think a little bit to know to put in the p and q for those plus c's, and then solve for p and q was just simultaneous equations again. Now, the second part of the question asks for when the velocity is at rest. So we're going to plug our p back in here. So our velocity is 3t squared minus 12t plus 9. That's our initial velocity. And when you are solving for it being at rest, that means the velocity is 0. And if you notice, they're all divisible by 3. So that gives us t squared minus 4t plus 3 equals 0. And now we can factor this quite easily. T minus 3, t minus 1 equals 0. So at t equals 1 and at 3 is where our velocity is 0 or at rest. Okay, t equals 1 and t equals 3 And these are our two answers for there. So I hope you're starting to understand how these work. When you get to these questions, again, start with acceleration to determine whether you use the calculus formulas or the SUVA algebraic formulas. Draw your diagram, give you a little bit of spatial orientation. And with the calculus, you got to derive or integrate to get your different equations. Pay attention to the plus c's with respect to what's going on at the initial conditions. And also really pay attention to those positives and negatives with respect to the orientation or the origin. That can help you not get so confused with those signs that show up. Okay? Well, I hope this is helpful, and we'll have a video part 3 where I'll kind of recap both the SUVA and the calculus, and also show you a problem where you have two particles, one following SUVA and one following calculus in the same problem. So you got to make sure that you keep those separated in what's going on. So that will be in part 3, and I hope to see you later. Thank you again for joining me in the Zoom room.